Good morning, students. Today, I would start with part 4 of complex number. Up till now, we know what is a complex number is. We define what is a complex number is. We defined algebra of complex numbers. We also defined the modulus and amplitude of a complex number. Today, we start with complex cube root of unity. Now, with our basic secondary knowledge, if my question to you is, what is cube root of 1? Your answer would be 1. If you answer that 1 is cube root of 1, your answer is correct as far as real numbers is concerned. But if you consider complex number in general, then your answer is partially correct. Similarly, if my question to you is, what is cube root of 27? Your answer is 3. 3 is correct if our basic concept is of real numbers only. But in terms of complex number, it is partially correct. So, if 1 is cube root of 1, what are the other cube roots of 1? That is our area of discussion today. That means I have to determine value of cube root of 1. I start with let x is equal to cube root of 1, and I would determine different values of x, cubing both sides. X cube is equal to 1. I have cubed both sides, so the value x cube is equal to 1, which may be further written as equal to 0, that is x minus 1 into x square plus 1 is equal to 0. That means I consider x to be the cube root of 1 and start with this particular equation. After cubing, I am having two factors, that is either x is equal to 1 or x square plus 1 is equal to 0. That means I have obtained that one of the values of this particular equation, the cubic equation, is 1. And by seeing the cubic being a cubic equation, it is clear that there is not only one value of x, there are three values of x. What are the other three values, other two values? Because I have determined the first value. Therefore, first value I have determined x is equal to 1. And what are the other two values? We are about to proceed. That is x is equal to minus 1 plus minus root over b square minus 4ac by 2 into 1. So x is equal to minus 1 plus minus 3. I rewrite it in this particular form. So therefore, This is where our concept of complex numbers is helping us. One value we have already calculated. We have now determined two other values. One value is -1 plus I root 3 by 2, and the other value is -1 minus I root 3 by 2. Complex number was not known in class 10. That is why this area was neglected, as complex number is now known to us. So therefore, our value of x is -1. These two values plus this value are the cube roots of unity. You have to keep that in mind. One is said to be the real cube root of unity, and these two values are said to be complex cube roots of unity. We consider omega. Let omega is equal to -1 plus I root 3 by 2. I consider one of the cube roots as omega. After considering omega, I square this. I root 3 by 2 whole square. Omega square is equal to 1 minus 3 minus 2 I root 3 by 4. That is, omega square is equal to -2 minus 2 I root 3 by 4. It is equal to -1 minus I root 3 by 2. Observe this, that when I consider omega as one of the roots, one of the cube roots of unity is omega, and I square that out. On squaring, I am getting the value which is the other root, -1 minus I root 3 by 2. Therefore, you would conclude 1 omega square are cube roots of unity. 1 omega square are cube roots of unity, where 1 is the real root and omega square are the complex cube root of unity. So therefore, 1 omega square, this is the real root, and these two are the complex cube root of unity. So therefore, if you were answering 1 as cube root of 1, you were partially correct. Now, with omega and omega square, this is the complete cube root of 1. 1 is the real root, and omega square are the complex cube root of unity. Similarly, if your question is what is the square root of 8, you would conclude 2 omega square are the cube roots of 8. 2 is the real root, 2 omega and 2 omega square are the complex cube root of 8. Similarly, for 27, I am citing second example. 27, 3 omega square. So therefore, we are determining cube root of 1. No more 1 is the solution. The solution are 3 in number, not 1. And we proceed and determine the values. One value is omega and the other value is omega square. There are two properties of omega. First property is property 1. Property 1. Omega cube is equal to 1. Omega cube, property 1 says omega cube is equal to 1. If omega is complex cube root of unity, omega cube is equal to 1. You can easily determine its value simply multiplying these two. If you multiply omega square into omega, omega cube. And if these two are multiplied together, omega square into omega is omega cube. This into this is 1. And our second property is property number 2. 1 plus omega square is always equal to 0. If I add up 1 plus omega and omega square, the value is always equal to 0. So therefore, from now on, it is clear that cube root of 1 is no more 1. It is 1 omega square. 1 is the real root. Omega and omega square are the complex cube roots of unity. Similarly for 8, 2 real root, 2 omega square are the complex cube root of 8. Similarly 27, and a general example I am about to give you, if it is m is any number, then the cube roots are m to the power 1 by 3, m to the power 1 by 3 omega, m to the power 1 by 3 omega square. This is how we deduce the cube root of unity, and other examples are there. And these two properties, that is omega cube is equal to 1 and 1 plus omega square is equal to 0, are the two properties we would use while working out problems on the basis of cube root of unity. So as far as theory is concerned, we have covered theory portion of complex numbers. Now we would start with problems on complex numbers. Problem number 1. Express one by 1 minus cos theta minus I sin theta in a plus ib form. Now, this is by problem number 1, and I have found out that students generally do not simplify, do not determine value of a and b. I have to determine when it is said express in a plus ib form, it is that you need to find the value of a and value of b, or in an associated added condition may be given, find the value of a square plus b square. How do we do that? This is our complex number 1 minus cos theta minus I sin theta. I multiply this particular complex number by its conjugate. What is conjugate? Z is equal to x plus iy, and its conjugate is z bar is equal to x minus iy. I multiply numerator as well as denominator by its conjugate, that is 1 minus cos theta plus I sin theta divided by 1 minus cos theta I sin theta into 1 minus cos theta plus I sin theta. That is 1 minus cos theta in the numerator, I sin theta, and in the denominator 1 minus cos theta whole square plus sine square theta. After multiplying numerator and denominator by its conjugate, my denominator is 1 minus cos theta whole square plus sine square theta, and numerator is this. Further simplification, 1 minus cos theta plus I sin theta, and in my denominator would be 1 plus cos square theta minus 2 cos theta plus sine square theta. Sine square theta plus cos square theta is equal to 1. So 1 plus 1 is equal to 2. That is, I may write this as 1 minus cos theta plus I sin theta divided by 2 minus 2 cos theta. I have simplified that 1 plus cos square sin square is 1, 1 plus 1 is 2, 2 minus 2 cos theta. On further simplification, 1 minus cos theta divided by 2 into 1 minus cos theta plus I sin theta by 2 into 1 minus cos theta. Now these two get cancelled. And my real portion is half. 1 minus cos theta gets cancelled. So the remaining is half. Now when it is half is there, I move on to the imaginary part, that is plus I into 2 sine theta by 2 cos theta by 2 by 2 into 2 sine square theta by 2. This is some multiple angles. This part is part of trigonometry. That how can I replace sine theta in half angle form? Sine theta is there, but I am expressing it in terms of half angle. Sine theta may be written as 2 sine theta by 2 into cos theta by 2, and 1 minus cos theta is 2 sine square theta by 2. If you have not done this particular portion, you may revise or go through the formulas or write it sidewise, that this is equal to this for the time being. What I find is 1, 2 gets cancelled, 1 sine, another sine gets cancelled, left over is half into cot theta by 2. I have reduced this given complex number into a plus ib form. I have reduced this particular complex number to a plus ib form, that is a is equal to half and b is equal to half cot theta by 2. I repeat once again, given complex number multiplying by its conjugate, further simplification, very simple this is. Try it by yourself. After copying this, try it 2-3 times so that you gain confidence while working out problem. And then on further simplification, I break this up into half angle. The reason is, do not leave in this particular form, as it can be cancelled. Further simplify this. I simplify and cancel out this. Left over is cos theta by 2 sine. Therefore, A is half and B is equal to half cot theta by 2. I move on to problem number 2. If A is equal to A is equal to 1 plus I by root 2, find the value of a to the power 6, a to the power 6 plus a to the power 4 . So therefore, value of a is given and I have to determine value of a to the power 6, a to the power 4 plus 1. Value of a is given. So I find this is also multiple of a square, this is multiple of a square, and so is that I first and foremostly determine value of a square. So therefore value of a square is a square 1 plus I by root 2, a square is equal to 1 minus 1 2I by 2, that is a square is equal to, very simple, I have determined value of a square. So value of a square is coming out to be I itself. So the value of a square is I. Therefore a6 plus a4 plus a square plus 1 is a square whole cube, a square whole square, a square plus 1. A to the power 6, a to the power 4, a square plus 1, I am expressing in terms of a square. What is a6? A to the power 2. And now I replace value of a square. Value of a square is I. That is I whole cube, I whole square, I plus 1. I am now replacing value of a square in this particular expression. It is not an equation. Students generally refer to this as equation. No, it is an expression. Expression when equated to 0 is an equation. So the expression now reduces to the form I square into I square into I square, I plus 1, that is minus I minus 1 plus I plus 1. These two get cancelled and these two get cancelled. Left over the value of a6 plus a square, a to the power 4 plus a square plus 1 is equal to 0. I repeat it once again. Value of a is given. I find in this particular expression a to the power 6, a to the power 4, all are multiples of a square. I first determine what what is the value of k square, that is I, on replacing each term, because it is expressed in terms of square, I replace their values and the value of this expression is equal to 0. So therefore, given value of a and given value of the expression is 0. I now move on to problem number 3. If z is equal to x plus iy and mod 2z plus 1 is equal to z minus 2i is equal to z minus 2i, show that 3 into x square plus y square plus 4x plus y is equal to 3. Yes, this is my problem number 3. This problem now deals with modulus of a complex number. So given condition is, first you have to understand what is given. Given is a complex number z, x plus iy. Second is the equation that is in modulus form, and from there we would have our required condition. So I start with z is equal to x plus iy, therefore 2z plus 1 is 2 into x plus iy plus 1, which is equal to 2x plus 1 plus 2iy. Now there is a point out here that 1 is a real number, 2x is a real number. I combine it together to express as 2x plus 1. And my imaginary part is 2iy. So therefore 2z plus 1 is equal to this mod of 2z plus 1 is equal to mod of 2x plus 1 plus 2iy, which is equal to root under 2x plus 1 plus 2y whole square. So therefore, in 2x plus 1 is a complex number. It has real and imaginary portion. You should not get confused. And what is modulus? Modulus is squaring the real portion and the imaginary portion. I square it. And therefore, this is equal to this. I mark it equation number 1. I start with the second portion. Z minus 2i is equal to x plus iy minus 2i. Subtracting minus 2i, that is x plus I into y minus 2. Z minus 2i is a complex number, and when it is a complex number, it has a real portion x and the imaginary portion is y minus 2. So therefore modulus of z minus 2i is equal to root over x square plus y minus 2 whole square, squaring the real portion and the imaginary portion, and I mark this by number 2. By the given condition, this and this is equal. So from 1 and 2 root over 2x plus 1 plus 2y is equal to root over x square plus y minus 2 whole square. Therefore, you can easily write this as squaring both sides 2x plus 1 plus 4y square x square plus y minus 2 whole square 4x square plus 1 4x 4y square is x square plus y square 4 minus 4y. I transfer all of them to my left hand side 4x square, that is 3x square, 4y square, that is 3y square, 4x minus 4y plus 4x plus y, and here it is 4, here it is 1, that is equal to 3. Therefore, our required result plus 4 x plus y is equal to 3. Very common problem there in your different examinations. Practice these types of problems. There may be other condition added to this. So I repeat it once again. 2z plus 1 is a complex number. Z minus 2i is a complex number. And if both of them are complex number, this is the modulus of a complex number, and modulus of a complex number, I start with 2z plus 1. On further simplification, I get equation number 1, which is modulus of 2z plus 1. And similarly, I find out the complex number z minus 2i. Its modulus is this. Both from 1 and 2, I'm adding, because this is the given condition. This is the given condition of the problem itself. I am using and substituting and on squaring and simplification. This is our required result. I now proceed to problem number 4.